So if you may recall, we had actually tried to solve this particular circuit. So this circuit consisted of 2K and 4K resistances connected along with this capacitance. And we had further resistances connected along with this. So let me probably redraw the circuit once again, or let's continue with the same page here. Okay, so let's see how the circuit was. Again, we had a capacitance which was pre-charged to 17 volts. And the current that was flowing in this branch was designated as I. And this was a 9 microfarad capacitance. And we had one resistance here, another resistance here. And this was 2K and this was 4K. And this particular node was designated as A, this was B, and this was C. And here we had one more resistance, which was 3K. And the equations, I'm just continuing from there, but I'm just redrawing the circuit so that the markings I had made on that day, that doesn't confuse. That is the reason why I'm doing this. Okay. So this is problem number 3, what we had seen on Monday. Okay, so what was asked was we had to solve for VA, VB and VC. Okay, and also certain currents. This is what was asked. And we wrote, first of all, we started with writing the nodal equation. So this capacitance was a 9 microfarad capacitor with a 17 volts initial charge, and the current flowing through the capacitance was designated as I. That's what was done. So we had written the equation for node A, node B, and node C. This is what we had done. KCL we had written. So for node A, we had written 6 VA, right? Minus 3 VB minus VC, because we had simplified whatever we had written along with, for example, VA divided by 3K, VA minus VB by 2K, and VA minus VC by 6K. That's what we had written, and that I had simplified like this. Okay, and node B we had written minus 2 VA, okay, plus 3 VB and minus VC equal to 4I. But this was milliamperes of current, because kilo ohms of resistance will result in 1 volt divided by 1 kilo ohm. We are going to get only 1 milliampere. The third one was minus 2 VA minus 3 VB plus 6 VC equal to 0. These were the 3 equations we got. So let me designate this as equation number 1, and this as equation number 2, and this as equation number 3. Okay. So let me try to, because I have to solve for VC ultimately, whatever is the voltage across the capacitor. We have to solve for, first of all, voltage across the capacitor. Okay, first thing we want to do is that. So this is essentially same as node B voltage. This is the node B voltage. Both are one and the same. So let us try to first of all eliminate maybe VA and VC. That will actually help us. So let me first do equation number 3, whatever is equation number 3, that is having 2 VA. So let me first of all compare that with equation number 1. So equation number 3 I will multiply by 3. So let me try to get that. So that is going to be 6 VA, which is minus 6 VA actually, and minus 9 VB. And I'm going to get 6 multiplied by 3, which is 18 VC equal to 0. So this is going to be equation number 3. And what is equation number 1? Equation number 1 is 6 VA minus 3 VB minus VC equal to 0. This is going to be equation number 1. So let me add these two. I'm going to get minus 12 VB, right? And plus 17 VC equal to 0. Let me call this as equation number 4. Okay, so this is having only VB and VC. So the next one I'm going to do is again equation number 2 and equation number 1. If I compare and if I try to eliminate VA, again if I want to eliminate VA, I should be able to do that. So let me try to first of all multiply equation number 2 also with 3. Okay, so I'm going to multiply equation number 2 with 3. So that is going to be equal to, so this is minus 6 VA and I have to multiply by 3. So that is going to be 9 VB minus 3 VC equal to 4 multiplied by 3, that is 12 I milliampere. So this is same as equation number 2. And let me write again equation number 1, which is 6 VA minus 3 VB minus VC equal to 0. That is equation number 1. So let me add these two. If I try to add these two, I'm going to add these two equations. So I'm going to get 0 here. And when I add this, this is 6 VB, right? And I'm going to get 3 plus 1, so that is minus 4 VC, okay, equal to 12 I milliampere. So let me call this equation as equation number 5. So if I just compare these two, right? So let me first of all write this in a simplified manner. This is going to be 3 VB minus 2 VC equal to 6 I milliampere. So this is going to be same as equation number 5. So can I compare equation number 5 and 4 and then eliminate VC so that I would be able to get everything in terms of VB. So if I try to eliminate VC, I have to multiply this by, let's say, 8.5 and just multiplying by a fraction. Okay, so this is 3 8s are 24 and 25.5. So I'm going to get 25.5 VB. Okay, and I'm going to have minus 17 VC equal to 6 8s are 48. So this will be 51 I milliampere. So this will be same as equation number 5. Okay, now when I add these two, I am going to get what? So this is going to be 25 and 12, so 13.5 VB, which I can write as 27 by 2. That's also fine. So I'm going to write 27 by 2 VB equal to, right? I'm going to have 51 I milliampere. So VB is going to be equal to 51 multiplied by 2 divided by 27. So I can say this is 17, this is 9 3s are 27. So I'm going to have 34 divided by 9 I milliampere. Is this clear? So if I look at VB is having 34 by 9 I. That is actually the voltage. 34 by 9 I. That is going to be the voltage. And after all, the current flowing here is I. So that means from here, from this two terminals, if I try to visualize what is the resistance of rest of the circuit, the equivalent resistance is going to be 34 by 9K. So I'm going to say that this circuit is equivalent to having, this capacitance, which is actually 9 microfarad capacitance, And if I try to look at this current as I, and this is grounded, and this voltage is 34 by 9I. That's what I'm saying. That means this resistance, what it is visualizing is 34 by 9K. That's what it means, because this is the milliampere what is flowing here. So I can say basically that this capacitance 9 microfarad, and this is VB. Okay, so if I try to look at what is VC, or I should say the capacitance voltage, if I may call this as capacitance voltage, is going to decay, is going to have a time dependent function, going to have a time dependent function, which is actually going to be whatever is the initial voltage multiplied by e power minus t by tau. That is how it has to be, because there is no other excitation function. There is no other exciting voltage. And the initial voltage is given as 17 volts, right? And I'm going to have minus t by tau, where tau is RC time constant, which is consisting of its own capacitance value and the resistance visualized by the capacitance itself. And we just said that the resistance visualized by the capacitance is 34 by 9K, because the current that is flowing is I, and the voltage what is seen here is 34 by 9 multiplied by I. So the capacitance is visualizing a resistance of 34 by 9K. So this is going to be 34 divided by 9, right? Multiplied by, and I'm going to have basically multiplied by C. C is basically going to be my capacitance value, which was 9 multiplied by 10 power minus 6. So 34 by 9K means multiplied by 10 power 3, and this has to be multiplied by 9 into 10 power minus 6. So this works out to 34 millisecond. So again, the time constant always has the dimension of the time itself, which is in terms of millisecond in this particular case. So I am going to have voltage of the capacitance, which is same as VB, voltage of node B. So this is the voltage of node B. That is going to be equal to the initial voltage, which is 17 volts, multiplied by e power minus t by tau, which is actually 17 multiplied by e power minus t divided by 34 times 10 power minus 3. So 10 power minus 3, when I'm taking it up, it has to be 1000 t divided by 34. And 1000 by 34 works out to something like 29.412. Please verify this. So this is going to be 29.412 times T volts. So this is the voltage of node B, which is also incidentally the voltage across the capacitance, which is decaying from 17 volts. So it is going to start with 17 volts and it is going to decay based on the time constant what we have. So this is going to be the capacitor's voltage.
Ma'am, how did you consider the 34 by 9 voltage to be resistance?
34 by 9 is the voltage. 34 by 9 multiplied by I is the voltage here. And what is the kind of current that is flowing here? That is I. So the capacitance is essentially seeing a resistance of 34 by 9K, because 34 by 9 is actually the multiplying factor which is actually visualized by the capacitance. The voltage is here, the voltage that is here is 34 by 9I. So if I consider these two as some terminal, okay, forget about whatever is present here. If it is just two terminals, it is like Thevenin's thing, basically. So this is the voltage which is visualized as 34 by 9 times I. And what is the current that is flowing here is I. So what is visualized as the impedance across these two terminals? That is the voltage divided by the current itself. So voltage divided by the current, if I try to see, that is 34 by 9 K, because we said this is milliampere. The current what we get is a milliampere. So that is the reason why the impedance visualized across these two terminals is the resistance or whatever that is being seen by the capacitance itself, which is connected across these two terminals. So this is as good as looking at the open circuit voltage or the voltage of the node versus what is the current that is flowing through that terminal. That is the reason why 34 by 9 is seen as, basically 34 by 9K is seen as the impedance visualized by whatever is the component connected across this. And the component that is connected across this is the capacitance. Okay, that is the reason why we are getting the time constant to be 34 millisecond in this particular case. Okay, so yeah.
I didn't get how you got 34 by 9K. How did you get the K?
Here, whatever we got, everything 6 or 4 or everything is in terms of K. The resistances are not just the resistance in ohm, it is kilo ohm. So everywhere we have neglected the factor of 1000. Otherwise, even these equations should have been written 6000 times VA, 3000 times VB, and VC, 1000 times VC equal to 0. Everywhere we had, when we wrote the equation itself, we just removed the K factor. K is essentially 1000. So obviously the current is going to automatically become milliampere. If you remove the kilo ohm and if you write that as just 6 and 5 and things like that, then the current becomes 1000th of that. You understand? Right? So that is the reason. That is the reason why when we express the current in milliampere, automatically the resistance is expressed in kilo ohms, not in ohms anymore. Right? Okay. So this happens to be my capacitance voltage transient, what the capacitance will experience. So this is 17 multiplied by e power minus 29.412. Now, if I want to know what is now VA and what is VC, I can use these equations, right? Because I have said minus 12 VB plus 17 VC equal to 0. So let me use that equation. Minus 12 VB plus 17 VC equal to 0. That was equation number 4. That is equation number 4. So I'm going to use this equation. So I can say 17 VC equal to 12 VB. And VB happens to be the voltage across the capacitance. So I have to just say VC equal to 12 divided by 17 multiplied by VB. So I can directly say this 17 I can remove. So 17 and 17 get cancelled. So I should say 12 multiplied by e power minus 29.412 T. This is the voltage that is visualized as the voltage of node C. This is the node C. Here is node C. So node C voltage is given by 12 times e power minus 29 whatever times T. Now what is VA? VA can be deduced either by using this equation or by using this equation. So VA definitely you can make use of either 6 VA minus 3 VB minus VC. So let us write that. 6 VA minus 3 VB minus VC equal to 0. This was equation number 1, what we wrote in node A. So I should be able to say 6 VA equal to 3 VB plus VC. So VB we got as 17 e power minus 29.412. So 3 times 17, that is 51 e power minus 29.412. 29.412 T. And VC is same as 12 multiplied by whatever we got here, e power minus 29.412 T. This is equal to 6 VA. So this is totally 63 e power minus 29.412 T. So we should be able to write VA as 63 divided by 6, that is 10.5 e power minus 29.412 T volts. Please note all these things are in volts. How will we get I? I is essentially C dVc by dt because that is the current through the capacitance. Or I should say D of V capacitor, not Vc means it's not voltage of node C, it is dV capacitor by dt. And what is the voltage across the capacitor? That is this. So I should say C multiplied by 17 d of e power minus 29.412 t divided by dt. So this is going to be, C is 9 microfarad. So I should say 9 multiplied by 10 power minus 6, right? And I'm going to say multiplied by 17 and multiplied by minus 29.412 into e power minus 29.412 times t. Right?
Ma'am.
Yeah.
Ma'am, I actually solved those 3 equations. I got
Mm-hmm.
VA separate as 7 by 3, ma'am.
You will have a transient. If you have not taken the transient, then you are not going to get that correctly because I itself has a transient. Please remember, I is not a straightforward algebraic, or it is not a direct value which is going to be, a number. You will not get I as a number. We are doing that now. We are solving for I. It will be in terms of I, and I itself is not a direct number. So if you had solved for VA otherwise, and if it is not coming out as a function of I, then it is not correct. It cannot be without. Yeah.
Ma'am, have you got VB as 34 by 9? Same way I solved in the same manner. That time I
We are
got
not getting
VA as
34 by 9. 34 by 9 times I. 34 by
okay.
9 times I. And I is a function which is going to be an exponential function in all probability. That's what we are solving right now. This is the exponential function which we are getting, which means I'm getting minus 29.412 multiplied by 17 multiplied by 9 multiplied by 10 power minus 6. the entire thing, which comes out to be actually 4.5 multiplied by 10 power minus 3 into e power minus 29.412. So if I remove this 10 power minus 3, I can write this as 4.5 multiplied by this entire thing milliampere. Okay, so I am getting this as 4.5 multiplied by e power minus 29.412 t milliampere. Please remember, this is a function of t. It's not a constant value. It is a function of t. So whatever you get as VA, VB, VC, you might have gotten in terms of I, but ultimately you have to solve for I. And solving for I was simpler because we got VB directly. Once you get VB, and from VB, you should be able to get the capacitance voltage function because VB is same as the capacitance voltage function. Okay, so that is why we had solved for VB in this particular case because VB is same as capacitance voltage function. See, the moment we involve R, L and C, all three of the elements. Please remember, this is also an energy storage element. This is also an energy storage element. Once we involve R, L and C, this is going to be a second order differential equation. So we are going to look at the second order differential equation or second order system now. So I'm going to introduce you to a second order system currently. So I can have a voltage source which is exciting R, L and C connected in series. This is one way of looking at a second order system. Or I can have a current source which is actually exciting R, L and C connected in parallel. Either of them can be called as a second order system. So in this particular case, I may write this voltage as V, and in this particular case, I can call this current as I. Okay.
And what's the difference? Why is it called second order system?
We are going to write the equation, then you would know why it is called a second order system. Okay. So if I call this as VDC, I can write VDC equal to R times I plus L times di by dt plus 1 by C integral I dt. Right? This is the equation that describes this particular Kirchhoff's voltage equation, what I have written here, mesh equation. This is the mesh equation which describes this circuit which is having R, L and C as its elements which are connected in series. Now if I differentiate this, so differentiating this equation, if it is VDC, dVdC by dt is going to be 0. So I can write that 0 equal to R di by dt, okay, plus L multiplied by d square I by dt square plus I divided by C. So this is a second order differential equation. I can write this as, if I try to bring down this L also, so I should be able to write this as d square I divided by dt square plus R by L multiplied by di by dt plus I divided by LC. This is equal to 0, right? So let me assume, because this has d square I by dt square, di by dt and I, everything in the same equation. Only function which is going to have a similar form for d square I by d square by dt square as well as d by dt as well as the original function itself is generally e power some st. I'm going to write this as some a e power st be the solution for this equation. Okay. So I'm going to have a solution of the form a e power st. So let me try to substitute that here. I'm going to first of all use this, which means a times s square into e power st plus this is going to be r by l multiplied by a times s times e power st. Plus I'm just substituting the value of, if I say that the solution is this, that means I equal to a e power st. That's what I'm assuming. So this is going to be I is substituted with e power st divided by lc equal to 0. Let me divide this equation by a e power st. So when I divide this equation by a e power st, I'm going to have s square plus r by l s plus 1 by lc equal to 0. Right? So this is generally the characteristic equation. Generally we call this as the characteristic equation for the differential equation what we have defined earlier. So let's try to get the solution for s. So s is going to be, this is a quadratic equation. So I should be able to get the solution for this minus r by l plus or minus root of r square by l square minus 4ac. So 4ac is 4 by lc divided by 2. So I'm going to write this as 2 and I'm going to write here as 4 and I can simply remove this 4 and I can write that as 1. So this is going to be the solution for s. Right? So this will give me for plus and minus, I'm going to get two things which are S1 and S2. So I'm going to get the solution as generalized solution. I can write I of t is going to be some constant A1 multiplied by e power S1t and another constant a e power S2t. It is a second order differential equation. So I have to get at least two initial conditions. I should be able to say what is I of 0 and di by dt at time t equal to 0. Both I should get as the initial condition. When I substitute those, I would be able to solve for what is A1 and what is A2. Okay. So the second order differential equation, what I had written in I, in the current, I would be able to get a solution somewhat like this. Okay. Now there are three specific situations which can arise here. The first situation is when r square divided by 4l square, right? That is going to be greater than 1 by lc. Okay, or I can write basically if r by 2l I am calling as some alpha and 1 by lc square root I'm calling as some omega. If I call this as alpha and omega, if alpha is greater than omega, in that case, whatever is under this root, this is going to be a positive quantity. So under this situation, I am going to have whatever is alpha square minus omega square, that is going to be a positive quantity. Okay, so square root of a positive quantity I will get as a real quantity. So I'm going to get S as alpha plus or minus I'm going to have alpha plus or minus square root of alpha square minus omega square. This is going to be a positive quantity.
Ma'am, is it minus alpha, right? Because it's minus r by 2l.
Yes, it is minus alpha. Thank you for correcting. Good. So minus alpha plus or minus root of alpha square minus omega square. So I'm going to call plus as say S1 and the minus quantity as S2. Okay. So I'm going to get the solution as I of t equal to e power whatever minus alpha plus or minus square root of, not plus or minus, I'm going to use the plus first and the minus next. So I'm going to say minus alpha plus alpha square minus omega square square root multiplied by t. This is multiplied by A1 and I'm going to say A2 multiplied by minus alpha plus minus root of alpha square minus omega square times t. So this is the complete solution for I of t. So both of them look like they are exponentially decaying function provided this quantity is not much higher than this quantity. Please understand, if alpha happens to be a very small number compared to square root of alpha square minus omega square, then this will become exponentially increasing, because instead of minus alpha, I would be having alpha square minus omega square root of that minus alpha. So in which case this will become exponentially increasing quantity, whereas this will become exponentially decaying quantity. Okay. The second case, if I'm going to have, this is case 1, when I'm going to have alpha square, r square minus divided by 4l square is greater than 1 by LC. Yeah. Case 2 is when I'm going to have r square divided by 4l square equal to 1 by LC. That is alpha square is equal to omega square. So in this particular case, whatever is the under root, that is going to vanish, because I'm going to have, this is going to vanish. So if this is vanishing, so this is equal to 0, I will have both roots are equal to each other, which is going to be simply r by 2l itself. So both roots S1 and S2 will be equal to each other. In which case I'm going to have A1 e power minus alpha t, and I'm going to have A2 multiplied by e power minus alpha t. This is going to be the function overall I'm going to get. But this will not be a complete generalized solution, because I will not be able to get a specific solution unless I substitute for both these initial conditions. And that is the reason mathematically we mention this as I of t equal to A1 plus some A2 times t multiplied by e power minus alpha t. This is the generalized solution normally we will write, because when you are doing the second differential, this will automatically become A2 times e power minus alpha t. So we will be substituting, we will be getting A1 with I of t at t equal to 0, and A2 will be getting by using di by dt at t equal to 0. Okay, so the first response what we got when we said r square divided by 4l square is greater than 1 by LC, here both S1 and S2 are going to be real. Okay, and we call this particular case as over damped response. And when we are talking about this alpha square minus omega square vanishing completely, we call this case as critically damped response. And this is really not much of importance because this is essentially something like a boundary condition at which it is transitioning from, the system is transitioning from over damped to the next case what we are going to discuss, which is actually case 3, where we are going to have r square divided by 4l square to be less than 1 by LC. So what we are going to get here is root of alpha square minus omega square. When I try to calculate, this is going to be a square root of a negative number. And whenever we are talking about square root of a negative number, it is generally square root of minus 1 multiplied by square root of this positive number, which is actually we have removed this minus 1 separately. So this is going to be I multiplied by square root of minus 1 is generally specified by I. But because we use I for the current all the time in electrical engineering, we are going to rather use the symbol J instead of I. J is square root of minus 1. And that is going to be multiplied by alpha square minus omega square square root, which is the actual quantity, only we are looking at the magnitude. So this is going to become overall root, if I try to write, S1 comma S2 are going to be minus alpha plus or minus I times square root of alpha square minus omega square. Okay, this is the case 3. So in case 3, if I try to write this, I have to write the solution as I of t equal to a1 e power minus alpha multiplied by, or I can remove this a1 and put a1 inside, and I can say a1 times e power, right, minus I times alpha square minus omega square, or I should be able to write this as e power plus I times alpha square minus omega square. So this is having two portions. One is completely real and the other one is the imaginary portion. And this particular thing is actually, expanded by Euler's formula. So the Euler's formula basically says that e power I theta is going to be cos theta plus I sin theta. So we are going to use this to expand this, which will give me I of t equal to e power, right, minus alpha t, of course, and then I'm going to have a1. Let us say if I call this entire quantity as some beta, this alpha square minus omega square square root as some beta. So I'm going to have e power minus I beta and plus a2 times e power plus I beta. So I can write this as e power minus, I have to of course put t along with all of these. So I should say a1 cos of beta plus j sine beta in one case. The other case is going to be A2 multiplied by again cos of beta t minus j sine beta t. Right? So these are going to be the two portions, and I should be able to write this as e power minus alpha t multiplied by a1 plus a2, which I can call as another constant, maybe a dash, whatever, multiplied by cos beta t plus a1 minus a2 times j sine beta t. But after all, what we are talking about here is a real current, actual current that is flowing through the circuit. So this entire thing should come up to be a real number ultimately. And similarly, this entire thing should also come up to be a real number. So I should be able to write this as e power minus alpha t multiplied by some c, constant c cos beta t and constant d some sine beta t. So this is actually an oscillatory function that we are going to get, which is having cosinusoidal and sinusoidal functions. And C I can write as some sine A, and this I can write as some cos A. So sine A cos beta t and cos A sine beta t will ultimately work out to be sine A plus B. Right? Sine A plus B. So which I can write this ultimately as e power minus alpha t multiplied by sine of some kind of beta t or beta dash t minus some other theta or phi. I can write this basically as a sine with some or cosine with some. Either way is fine. So this is going to be the overall solution what I get, and this has to be multiplied definitely by the constant. Whatever this phi can also be ultimately inferred with the initial condition. I have to put some other constant here, a or something like that. So there are two constants here. Please note this is one constant, this is another constant. So this particular thing is going to have a sinusoidal or cosinusoidal response, but with the peak slowly decaying. As time goes by, the peak will decay. So I am going to have the frequency here, frequency of the oscillation defined by this beta. And what is the starting instant that is defined by this phi, and at what rate it is decaying that is defined by this alpha. So I am going to have basically three types of responses possible for this kind of a second order system, which is defined by R, L and C in series, or R, L and C in parallel, because if I try to write the equation for this parallel circuit, I will have basically I equal to, I should be able to write V by R or C dV by dt, which is going to be the current here. Or I should be able to write this as 1 by L into integral I dt. Right? This is I, what I am supplying, not small I, this should be capital I. I am supplying a current here. So this particular equation, which is written in terms of Kirchhoff's voltage law, and this particular equation, which is written in terms of Kirchhoff's current law, both of them look exactly similar to each other. Only thing is, in one case it is node voltage which is taken into consideration, and here it is the mesh current which has been taken into consideration. So in either case, we are going to get a second order differential equation, and the second order differential equation has three types of responses possible. One is going to be both real roots. When I have both of them, both roots are real. In this case, we call this as overdamped response. And when only we have, that is, both roots are real and distinct, then we are going to have overdamped response. Now we have real root, but only one. In that case, we call this as critically damped response. And we are going to have two distinct roots, but complex. Real part is the same, but the imaginary part changes. So this one is underdamped, or we are going to have an oscillatory response. What I'm going to do in the next class is I'm going to take at least for two cases, overdamped and underdamped, because critically damped is when the circuit is transitioning from overdamped to underdamped or underdamped to overdamped. Only at one point it is going to experience this critically damped response. So experimentally, it is not going to be very easy for us to catch this particular response, whereas we would be able to see very clearly overdamped or underdamped response. So what I'm going to do is to take two cases, one case for overdamped and one case for underdamped, and I'm going to show you the response by simulating it in a particular software. So I'm going to take a particular value of R, particular value of L, and particular value of C, such that R by 2L is greater than 1 by root LC in the first case. In the next case, I'm going to take R by 2L is less than 1 by root LC. For both the cases, I'm going to show you how the circuit responds. Okay? And I would request you guys to look at a package called, the software tool called LT-Spice, which you would be using eventually. And one more software tool is available called PSIM. So PSIM is also available as student version, which is actually a free version that is available, that is downloadable from the net. LT-Spice is also completely free. So if you try to download either of them, you would be able to simply connect the circuit with resistance, inductance, and capacitance along with the voltage source or an initial condition of voltage across the capacitance. Then you would be able to see the response, what kind of current is being carried here. Okay, so let us try to simulate this with either LT-Spice or PSIM in the next class, so that we understand exactly how the response would be for either critically damped circuit or underdamped circuit or overdamped circuit. We'll try to look at this exactly how we get the responses. Okay, fine. Any questions on this?
Ma'am?
Yeah.
Ma'am, in the equation above the Euler's formula, you haven't mentioned the t ma'am, in the equation I of t. For the
it
third
should be definitely with I of t, obviously, because if I am saying S1 and S2 are this.
No, ma'am, I'm saying you haven't written in the equation.
See, I should say S1 and S2 are this. So if I'm going to say A e power S1t plus B e power S2t, obviously I have to multiply this by t. Here also I have to multiply by t, and I have to multiply this also by t. There is no doubt. If I have left out, I'm sorry about that, but it has to be definitely multiplied by t because we wrote the solution as a e power s1t or a1 e power s1t and b1 e power s2t. That's what we wrote as the solution to start with. So everywhere it should be multiplied by t. There is no doubt. Here I have multiplied by t. Here I have multiplied by t. Here I have multiplied by t. Right?
Yes.
Yeah.
Thank you.
Okay.
Below
Yeah.
you have
Yeah.
changed the I to J, right?
Yeah, because I we are mentioning as current generally in electrical circuits. So in mathematics, generally you will mention square root of -1 as I, but generally in electrical engineering, we write that as J. Small g. In electrical engineering, in any book, you would see J as the notation. You will see